Okay, so I start.
So we're happy to have Yegor from now in UC Berkeley to give us the talk on gray crossings and R-matrices.
Okay, thank you very much for the invitation to give a talk and also for the invitation to come to Berkeley. I'm really happy to be here. It's a fantastic place. And I'm going to report on some work I've done in recent years and some work in progress with these people. So the slogan so first the first thing I would like to say will be the sort of physics part, like physics introduction, the very first thing, and then very quickly, I will translate it into something more mathematical. So I hope it will be understandable on both sides. So the slogan is of this work is that there is an approach, certain approach to certain type IIB compactification, like a certain type IIB background, where branes are correspond to representations of quantum toroidal algebra. So it's usually denoted like this, but I'm going to say that it is just A. Otherwise, it's very difficult to write every time. Is it big enough? Is it visible? Like for most people? I mean.
Yes. Okay. It's okay.
Good. So, yeah. Okay. Good. So there are lots of representations of this algebra of different types, and it turns out that they have all of them have something to do with the corresponding zoo of branes. So branes in type IIB on star. So star is here. This is the star background. So what happens here? We have in total 10 dimensions, and there are 6 of them on which the equivariant group X. So I have added this is the synthesis to remind that there is a 2-dimensional torus acting on this. So it is C3 really, with the action of C star times C star squared. With the equivalent parameters given by Q, T inverse, and T over Q. And these are the parameters of the algebra, the deformation parameters of the algebra. From the very beginning, let me make an announcement that I'm not going to define the algebra to write any relations and generators, because they are very cumbersome and long, can be found in the literature. Otherwise, I tried this for several talks, and the problem is that the talk finishes before I introduce the algebra, finish introducing the algebra. So it's just a huge algebra. We can I can say a little bit more about its properties, but the exact definition, one can look it up just.
Not a good idea to define some objects like this by generating this relation.
Absolutely correct. Yes, it doesn't clarify much. The generators and relations are some big crazy stuff. So here I'm going to try to talk a little bit about the properties of the algebra and the representation theory of the algebra, and try to relate it to the Brane picture in this background. So mostly I will be drawing these 3 dimensions. So these 6 dimensions, they are going to be encoded in colors. So the different brane, so because there is an equivalent action here, so the brane should span fixed submanifolds. So fixed submanifolds are the sit at the origin of this C, each C, or they span the whole C dimension, the whole complex dimension. So this is the choice basically, and which one they span, like which C's they span, will be encoded in colors of the corresponding branes and the corresponding pictures. And so this part I'm going to draw on the blackboard. This is three-dimensional part, and mostly I will draw the two-dimensional part, the third part. So this will be on the blackboard plane. And this is S1, I forget about it, just I am not going to draw it, because everything will span this S1. So here there are different types of branes in type IIB string theory, and there are different representations of this algebra. Again, so the slogan is that whatever you draw in the setup, whatever is supersymmetric, again, I'm not going to go into the other side, so I'm not going to define the algebra. On the other side, I'm not going to discuss which supersymmetry is preserved and like which configurations, why they're supersymmetric, etc., etc. So first, the biggest reason for this is that I'm not an expert on this and I don't completely understand it. But so here's here's our first example. So there is this D5 brane. So there are PQ5 branes, and there is a green D5 brane. So it's going to be to sit here. So the color green in my language will correspond to this brane spanning CQ and CT inverse. So these are in total D5 brane is 6-dimensional. For like traditional reasons, and it's going to span 2 complex dimensions, so 4, and then this S1, which I told you that everything is going to span, so don't worry about it. And here it spans this RY direction. So D5 brane is also, you can say that it is, there is a PQ charge. It's in our picture will be 105 brane, also called 10 because 01. Because it will span this RY, and also because because of the reasons of supersymmetry, this slope, this direction in this XY plane should correspond to the PQ charge of the brane. So there is another example, bigger, and NS5 brane of similar green NS5 brane. So this is 10 PQ brane, and it's going to span, because it's green, so the green color has to do with this part of the geometry. So it's going to span the same directions here. But because the PQ charge is orthogonal, it's going to span here this direction. And this one again, so we can forget about it. So these are 2 examples. And what can one, so for now, what can one do with it? If you have a line, so here I start drawing this XY picture. So this is R2XY. And I'm going to draw, everything is going to be green. So the green one coming here, the D5 coming here, the NS5 coming here, so they can have a junction. And they do have, in type IIB, they do have a junction, which gives rise to a bound state, which is 1, 5 brane. So what happens in this right-hand side, on the mathematical side? So it was discovered by some time ago by Avatafegin and Sharaishi. There is the corresponding picture of of an intertwiner. So that is there is the same picture in representation theory, where two representations, you can take a tensor product of them, and in the tensor product, well, there is an operator from a tensor product to another representation, which which commutes with the action of the quantum group, or of this quantum toroidal algebra. Now, what are the representations corresponding to these ones? It turns out that there is a wealth of representations which exactly correspond to this. They have both the color part and they have this part in xy direction. So what corresponds to these ones? Let me write it here. So representation. So the representation here is a so-called Fock representation F with the corresponding indices. Probably I also need to write it in green, but let me assume that you remember that it needs to be green. So it's F01 with this parameters Q and T inverse. So it turns out that there are corresponding Fock representation for every slope here. Here it is 1, 0, and all of them come in three flavors, so in 3 colors. So here I can have the green one, and I can have the, say, orange one here, and the orange one, the difference is that it is going to be spanning CQ and C T over Q. And otherwise, in this direction, it's going to be the same as this D5. So it is still a 0-1 brane, just spanning different directions in the C part. And this corresponds to another Fock representation. So what is Fock representation? It is representation on a free, on a bosonic Fock space. Yes. Yes. I should. So here I write everything in white. So hence the subscripts, and here I double. Here is both the color and the subscripts, so that you keep track of those, because this will be important. So let me just first give an example where the color will be the same on the whole picture, and this will be the familiar case of like PQ brane webs, or like toric pictures in refined topological strings. In that case, the color will not play a role. It will be one and the same for the whole picture. But then, like what I'm going to talk about here, this brane crossing story, the color will play a role, because there will be different types of branes in this setup. So, okay, first of all, so here is this the archetypal example of an intertwiner. So there is a tensor product of F tensor F, the corresponding. So I'm not going to write here on the picture the indices, but there is a tensor product of these two. There is the second, the third one, and there is an operator acting from the tensor product. Okay, I better. Okay, the first time I write the synthesis here explicitly. So there is this 0, 1, the vertical one, 1, 0 here, and 1, 1 here, right? And all of them are of the same color, but the same indices. So there is the corresponding operator that's discovered by these people, which commutes most importantly. So if I have any element G of A, so A is a Hopf algebra. So the psi intertwines the action of G in this. Absolutely. So psi depends on them. Yes, and the physical meaning is not known. So say the vertical one. You say Let me denote it like this, so that it's how do you call it? The slope is here. The slope. So the coproduct depends on the irrational slope. Slope in R2. Sorry, irrational. So the vertical one stands for something like pi2 plus epsilon plus 0. So this is like one choice. But then there is an infinite number of them, and this is a whole different story, which I'm not going to discuss. I'm going to stick with one coproduct for this whole talk. So this one will be my choice. The vertical one also called like this. But in principle, all of these psi's, they do depend on the coproduct, and like this is a mostly unexplored story. Okay, so here is this picture of intertwiners. Now we can say that the branes, so the branes are representation, but when they join, so the junctions, brane junctions, I mean, intertwiners. So we only have so far one example discovered by these people, but the hypothesis, kind of the feeling is that whatever intertwiner one draws, there is a corresponding brane junction, a brane configuration. And like one can go along this route, trying different things, and verifying that actually they have like something to do with the corresponding brane. So what, first of all, like what does this psi operator has to do with this five brane web? So the physics, the connection between this physical part and mathematical part, but not just a picture, but kind of a quantitative connection. So if I draw something, a green picture, let me draw a green picture. Let me put it here. So let me draw some green picture corresponding to a, oh, it's another green, brighter one, okay. But still, like for me, it will be still a green picture. Something like this. This is a like PQ brane web or a toric diagram of a Calabi-Yau threefold. These are in physics language connected by certain like duality. But then what corresponds to it? Corresponds to it is a gauge five-dimensional gauge theory. Yeah. I have the preferred. I choose it for once and for all for this talk. It's an extremely interesting story how to change it. Like and don't understand.
There's some diagrams like this which don't correspond to five.
Yeah, absolutely. There is well, both sides. They're a little bit. There are 5D gauge theories which are not captured by the diagrams. There are diagrams which don't correspond to gauge theories. But there is a large intersection where they do. So there is. Sorry. And this 5D gauge theory, it has, well, it sits on, again, so it sits on the world volume of this brane. So it sits on CQ times CT inverse times this S1 about which we agreed not to care. So it sits on the world volume of this D5 and then S5, the green on the whole green picture. So the green picture has some of the dimensions which are drawn here, but the others which I didn't draw, which are the color, the ones encoded by the color, in which precisely lives the gauge theory. So and this gauge theory, so it's I can say even more. It's n equal 1 supersymmetric gauge theory. So it has a partition function, the Nekrasov partition function. Nekrasov instanton partition function, say z. And this is given by the some prefactor times the sum over some Young diagrams, lambda 1, lambda 2, and here are some factors, say z small, depending on lambda 1, lambda 2, and some parameters. So lambda 1 and lambda 2 are Young diagrams. Sorry, should write larger. So this label the states, so equivalent to the states lambda belonging to the green Fock spaces. So these are precisely the states in these representations which are on these legs. So lambda 1 and lambda 2, they are states on these intermediate edges. And when I sum over them, that's the sum over the complete basis of states in my representation. Moreover, so this z, the gauge theory partition function, is equal to how it is called, the contraction of my psi intertwiners. So I take psi, 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 and psi according to my picture, and let me draw it as a picture. So I connect them in the same way. Well, one can write it in the form of tensor products and contractions, but let me just, it's easier to, to draw them like this. So you contract them and then insert vacuum states on the outer legs, and then the answer is the same. So it's not just the combinatorial identity. So you sum over lambda 1 here, lambda 1, lambda 2 here, lambda 1, lambda 2 there. It's like the factors, they also coincide. So this instanton factor is reproduced by this psi's. And that's the connection between the theory living on the Brane and the intertwiner, the matrix elements of the intertwiner, the vacuum matrix elements of the intertwiners. Okay, so this is a sort of an old story. Now, what kind of distinguished intertwiners do we have? Others, like there is this triple junction, fine. So we can draw these green pictures and stuff. By the way, so there is no, you cannot change color here because for geometric, well, in this physics part, for geometric reasons, because the branes, sorry. So these two branes, they can merge because they have this part of the geometry. So everything except this Rx and Ry, they coincide. That's why the gauge theory lives on this part, this and this one. But if I say have, instead of this D5, I have an incoming orange vertical brane. It cannot form a junction with an NS5 brane. So whenever you start drawing something green in the picture, in this picture of junctions, and have these trivalent junctions, you are always going to have a green, at least like this part of picture, this disconnected part will be green if you draw it like this. However, one can ask, well, maybe we can have something more. Maybe we can have different sorts of intertwiners. And what? Well, first of all, what kind of intertwiners we have, and what kind of Brane diagrams can we have? So the answer is that we haven't yet used this R-tau direction. So this R-tau direction, in the picture so far, it hasn't played a role because, again, so this junction, it forces everything to be on the same value of tau. So they see that a point here and this, for them to join, these points should coincide. So in fact, there is a third direction here sticking out of the blackboard, which I haven't drawn here because everything is just at the same value of tau. But what if, I think, what if I have branes? So let me separate it. So branes at different values of tau coordinate. Then I can have something funny. I can have, let me now start drawing three-dimensional. So I have the plane of my picture, this x, y, and tau going here. So I can have a brane sitting somewhere here, like the one in y direction, which is the d5, the green d5. But then I can have another green and s5 sitting at some other value of tau. So if I then project it back on my picture, on the plane of the blackboard, they're going to be like this. I'm going to draw what I call a crossing of branes. So they are far apart in this tau direction, but in the projection they cross. It's a bit like integrable systems or like knot theory, where you can cross the strands without joining them, because it's three-dimensional space, okay? So what if I have this sort of course I can have two types of picture here, because tau, I can have this delta tau here, either positive or negative. So it can be either bigger or smaller than 0. And these are physically different situations. So I can have a picture like this, and I can have a picture like that. But they don't join. So the question is, what this picture, again, according to our slogan, this should correspond to some intertwiner. And of course, the look of the picture suggests that what this intertwiner is. This is an R-matrix acting in the corresponding representation. So we have here a D5 and an S5. So we have corresponding to them, we have the Fock spaces, just as we had before, 1, 0. And we naturally, because it's a Hopf algebra, it's it does have a universal R-matrix. It's quasi-triangular, and one can say that let us consider and let us check if we have an R-matrix acting from F tensor F to like inverted, the same thing inverted, right? So there is an R-matrix acting in the tensor product of two Fock spaces like this. How do we find this, and how do we check that this makes any sense? Well, the answer is that actually it looks like this. So in this setup, nothing actually depends on delta tau. So delta tau. Well, I'm not going to explain why it is so, but it's kind of plausible thing. So it depends on delta tau in a piecewise constant manner. So that if delta tau is positive, there is one operator, and if delta tau is negative, it's another operator, which is like, again, physically or geometrically, it's kind of a natural thing to think about. But then, what do we have? We can take a limit of this picture. So how do we check, compute R? So we can send delta tau to either plus 0 or to minus 0. So we can have two different limits approaching the situation where there is a junction. And when there is a junction of two branes, then we know that we are back to these green pictures which lie in the same plane, like here. So these green pictures lying in the same plane, they contain something very similar to this crossing. So when this happens, so I break the boundary here. Yes. It's a piecewise constant dependence. So no. It's not a kind of. It's a geometrical thing. Like if I send delta tau to 0, this means that my lines are going to intersect now. That's the only thing I want to say. That they start intersecting, and from this I can sort of resolve the crossing.
Usually, for this set of algebras, I think we usually think about R-matrices as a
Yes, yes, they do have. That's the whole thing which I I skipped because the only trace of it remains here. I have this Q parameter. So this Q parameter is actually the ratio of spectral the ratio of spectral parameters U1 over U2 of these two states. So I have U1 lambda 1 and U2 lambda 2. So in fact, all these F spaces, they all have spectral parameters with them. So there is some, say, W, U, and here it is fixed to something like WU, if I remember correctly. So yes, it's an R matrix with a spectral parameter, precisely. So here I should have the same. So when I do the like do this limited, it's an R and R inverse.
Oh, okay.
So R and R inverse, which makes perfect sense like this. So, and if I do this limit, so I arrive at something like this, in quotation marks, because there are actually two types of this picture for plus 0 and minus 0, because and they are just equal to these two different R matrices. But then, in fact, what one can do, this is in quotation marks, but what, so this arrow represents a little bit of a leap of faith, like you have to believe. So this thing is something, but then what does exist is this sort of a resolution. Well, in the language of toric diagrams, it's a resolution. In the language of five branes, it's just a pair of junctions. Okay?
So can you just back up a second?
Sure.
And tell me what you associate the R. So these small modules, they were like, from what I recall, they were semi-infinite. I mean, sorry, the infinite branes.
Yeah.
They were just like straight lines.
Yeah, they're straight lines.
Corresponds to what? One diagram?
To this one. This one is R, and this one is R inverse. So this circled thing is going to be an R matrix. Okay, so I have this resolution here. I made some.
In which sense are the inverses are talking?
Well, just they are inverses. So there is a. Inverses.
I mean, is there some product that's identity?
Yeah.
And what is the product of that?
Well, it exchanges the Fs. So one exchanges them one way and another exchanges them the other way. And that's kind of, you can take a composition and it gives more or less identity, if I remember correctly.
I'm confused with the first thing. This is the spectral parameter kind of refers to sort of like the position of this line.
It's the position perpendicular to this line.
If they're already perpendicular, there's no sense of their position.
Well, the dependence on U and W is sort of stupid here. It will be something like U power. If you take a state here lambda and state here mu, it's the R matrix is going. I'm sorry, it's non-legible. I have to write better. So R is proportional to something like U power lambda minus mu, and that's it.
But it's just because it sits on infinite slope. So it's not the.
Well, I can let me see.
If there's a finite slope R matrix, it's very complex. Or it's just the.
I think it might have to do with the fact that they are perpendicular, and that one of them sits on the precisely is on the slope of the corresponding to the product. So of course, for a different direction, if I have something here of arbitrary slope, it would be a lot more complicated, probably. But I have nothing to say about them. But the thing here is that the dependence is really primitive because you see. So there are okay. sorry. So I may return to this a little bit later. So so I take this sort of I change. I have the modulus delta tau here. The modulus space. Let me draw the modulus space of this configuration of two branes. I think I have another blackboard. Or no. Yeah, okay, I just erased this once. Sorry. So the modular space or parameter space, well, in this case, it's nothing fancy. It's just the space of this green D5 and green NS5. D5 cross, well, okay, D5 plus NS5, the crossing. What does it look like? I have this delta tau parameter, and there are two. There is the distinguished point 0 here. And then at 0, I can resolve them like this, so that I have there this Q parameter, which is, sorry, which is more or less this distance. So it's, say, W1 over W2. So this is the Q parameter here. But then it turns out, that's, when I said that I have two different limits to +0 and -0, this actually means that this branch, this one-dimensional branch, is in fact not continuous here. So it sticks into this Q part in two different points. So when delta tau goes positive, it tends to one point in Q, which is Q equal to T over Q square root. And the other point here is vice versa, so Q over T square root.
I think it would be helpful if instead of interpreting things, you actually told us properties of this R-matrix.
Yeah, sure. So yes, sure. So this R-matrix, it satisfies.
If I take some kind of name product of those, whatever I imagine
Yeah.
would be, I don't get anything less identity. Tell us how to either work with them or characterize them.
Yes, so they satisfy Young-Baxter equation, first of all. So if I have a picture like this, then, or like that, then I can, they do satisfy the Young-Baxter equation. With the corresponding,
Which says what?
that there is here an R-matrix in two parallel Fock spaces, which like one can compute from the universal R-matrix, for example, which does the following. So I have W1, W2 here, and here I'm going to have W2, W1, and this R here. Like this. So this is the Young. It satisfies the Young-Baxter equation. That's the characteristic property of the R-matrix. Or like, because the R-matrices are different, you can say that it is R-T-T relation. So you can say that this is a T, this is R.
At 90 degrees, right? So I don't see how to make the unit vector kind of move with things that are at 90 degrees to each other.
Okay, so this is like an integrable system. So,
I'm saying the following: there exists an R-matrix on these block modules,
yes.
which is just a mathematical object, and you're trying to interpret it into branes. Is that the way it's called?
Okay, yes, you can say it like this. You can say it like this. That the mathematical statement is that there exists an R-matrix like this, and there is an explicit formula for it.
Okay, and you're trying to give us.
Maybe what's the explicit formula?
Sure. Yeah, let me. Yes, let me just write the formula instead of drawing a million of pictures. It's better to write the formula. So. Yes. So I write I write a matrix element of it along the vertical space, lambda and mu here. So, and it will depend on U and W, the spectral parameters. So as I promised, the dependence on U is elementary. Well, actually, the dependence on V is 2, but some prefactors here. Well, these are just prefactors. But to be concise, let me put them. So. And then comes the operator acting on the horizontal line. So I've put these states here, lambda and mu, and then it's an operator acting on in the Heisenberg space, in terms of Heisenberg generators. So here I have AN. So let me explain the notation here. ANs are Heisenberg generators. So AN, M, they satisfy the Heisenberg algebra. A little bit deformed. And then what is N? Okay, it's a prefactor. It's well, there is an explicit formula. It's the Nekrasov factor, which features in the Nekrasov partition function. So there is an explicit formula, but okay, let me not write it. Then this character is just the sum over cells of Young diagram like this. And these are some prefactors, which again, I'm just to not to make it infinitely long, let me skip them. So this is the explicit formula for this type of R-matrix.
So in it, there is no Q, the Q that you have there, or there is?
Q large
Sorry.
or Q small?
Okay. And now your proposal, and I view this as an operator that acts from, that's labeled by lambda and mu, and it acts on the,
Yeah.
on the two sides.
Right, yeah.
Why is it so asymmetric in Dublin?
Because of the coproduct, the choice of the coproduct. It's actually not too asymmetric in U, because if you take a matrix element here, suppose I put here two states,
Okay.
then it's the same. So in U and W it's symmetric, but it's not symmetric at all in this lambda and the state here because of the choice of the coproduct. So here's the formula. Again, look, you're completely right that what I'm doing is actually I'm taking an explicit formula for this R and interpreting like it in terms of some branes, which maybe like the essential part is this one. So this is the R-matrix for this cross branes, and the main idea was that it can be obtained as the generation of that picture, resolved conifold-like picture there on the upper blackboard.
For special value of Q.
For those special values of Q, which I've told you, like this Q over T plus minus 1/2. And one of them, I don't remember which one, is this one. And the other one is going to be other sort of inverse.
So what's surprising about this formula, right, is that anything that I could imagine in the string theory coming at some special values of Q would essentially be a delta function that's only supported where lambda and mu are basically the same or somehow correlated. And you say this, is it?
Yes, so it's the story which puzzled me also for a long time. So this really happens for T equal Q. For T equal Q, everything is trivial in the sense which you have just described. So if T, let me comment on this. So comment. If T is equal to Q, then R lambda mu is, first of all, it's proportional to delta lambda mu, and then it is an identity operator in F. So it's trivial. So if T equal Q, then it becomes trivial, and the naive expectation kind of that if the branes don't intersect, they pass through each other, and they don't touch, that it should, there is no interaction, there shouldn't be any interaction between them, so there should be a delta function here. So this is correct. For T equal Q, everything here, it becomes trivial. That's how it goes. But for T not equal to Q, we have a situation which resembles very much Chern-Simons theory, or 4D Chern-Simons, like whatever, because there are spectral parameters here. But the branes which don't talk to each other naively, they still do talk to each other, and they do feel that if they cross in this way or that way, just as in Chern-Simons theory. Well, again, it's kind of just a similarity. It's not that I imply that it is a Chern-Simons theory.
And the Berkeley satisfies only for the special value of Q?
Yes, yes. There is what is called an anomaly. If you put here, again, so all the pictures are green. So if you put here something like this, suppose I imagine this is R whatever, R tilde, okay? Depending on Q now, arbitrary parameter Q. And now I start checking Young-Baxter equation for this. It turns out that this isn't satisfied in a kind of trivial way. There is a prefactor, but a non-trivial prefactor which depends on all W1, W2, and all the parameters, all these Q parameters. There is kind of an anomaly prefactor depending on W1, W2, Q, and that's it. So, and it becomes trivial precisely when Q is equal to these two special values. So the anomaly is cancelled. Again, quotation mark anomaly. But it's true that it is satisfied for this q, precisely these values of q. Okay.
She tried the full, not the index version, like the full occurrence version. Tried that?
No, I didn't try, but I have something to say about about it, like vice versa. Like, sorry. No, the short answer is no. I didn't try. So, okay. So we have this type of crossing. What I would like to talk about a little bit more is a type of crossing which cannot be obtained from the, because from the, actually this formula, it's not a kind of, it's not a product of any, I mean, clever computation. It's a convolution, it's a contraction of two psi's, which psi's are explicitly known, so the convolution of them is explicitly known, and then you just plug in this, the only thing is to plug in this q, the special values of q, which basically goes into here, and that's it. So they...
So your basic objects are those guys over there, and then you observe that the special values of q, you get a factor equation. Otherwise,
yeah.
And when it fails, how complicated are three factors? You say
this epsilon prefactor.
You said that there's an anomaly. How complicated
It's absolutely manageable. It's
is it an monomial or?
No. It's a double hammer something. It's not an elementary function, but it's absolutely manageable. It's explicitly known. So that's a function. Sorry, one final comment. So comment number one. Sorry. Comment number one is that if t is equal to q, everything trivializes. Comment number two is that for t not equal to q, this n lambda introduces a selection rule. So lambda and so many matrix elements they vanish. So sorry, let me put this comment here. Comment number two. So for t not equal to qn, lambda mu of q over t is 0 for lambda, which is so when mu is not smaller than lambda, this prefactor is 0, so the matrix element is 0. So when this has only non-trivial elements when mu is smaller than lambda. So if you, for example, compose a bunch of these R-matrices like this, then the diagrams are becoming either stay the same or becoming smaller and smaller. So in this way, also one can notice that taking a trace over the subspace is sort of kind of a simpler thing than it looks, because well, if you take a pair of them and then take a trace, it turns out that the only possibility is a diagonal matrix element. So this is the comment, the selection rule.
And the unboxed equation is that you can exchange those two parallel lines?
Yeah, correct. Yes, you can exchange. So
in the exchange, there's also some reordering in the third direction. How do you interpret it?
this one, no, you don't do anything in the third direction. Yes, it's just an exchange. So let me talk a little. Okay, I suppose that this R-matrix, well, there is some basis for it. And then I was thinking about something which cannot be obtained from the junction, which is exactly, sorry, so let me bring back this one. No, it's gone. Anyway, sorry. So I had an orange brane. So I would like to ask myself, what is this type of crossing? Because this is perfectly valid from the point of view of the geometry of string setup. Because you can have a pair of branes, again, in 3D space. One of them is one color, another is another color at some different value. This is still something. But the problem is that you cannot do this naive thing which I did for this and degenerate into the crossing and resolve the crossing and say that everything is known in terms of this this triple junctions. So here there is no triple junction. Here cannot be obtained from triple junctions. Sorry? Okay, so let me redraw the picture. The directions in the 10D space. So I have green D5, say green D5, which spans these directions. And then there is an orange D5, which spans these directions. And then there is a green NS5, which spans, so the color encodes this part of the geometry. The flavor or color part is this. Like this. And then there is, and of course, an orange NS5, which goes like this. I apologize, I shouldn't have erased this part. So this 3D space which we draw, so this one is the blackboard on the blackboard. And this one is encoded by the color. So here is tau, here is x, here is y. That's the picture. And it cannot be obtained from triple junctions. So there is no possibility to degenerate it and then resolve it and have just to do this sort of like straightforward computation of contracting tube size. But still one can ask, is there an R-matrix acting in this pair of spaces? And the answer is yes. One can obtain it directly, but can be obtained directly from the intertwining condition. Or from universal R-matrix in some cases. There are basically two ways to compute an R-matrix in a given representation, in a given pair of representations. Either you solve directly, solve directly this equation. Of course, again, everything depends on the coproduct, like which I've already chosen. So either you solve directly from this condition, or there is a universal R-matrix which needs to be specified. So this R universal. If you specify to this tensor product of the corresponding Fock spaces, the green Fock space and the orange Fock space, and then if you are lucky, then you can calculate an explicit formula for that. So I took that route, and one can solve for it, get an explicit answer. Let me write it again. Let me write an explicit formula. This tensor product is irreducible. Yes, I think so. I haven't proved that, but okay, it's a good question to prove. From string theory, it should be that should be the case that the tensor product should be irreducible, but I haven't proved it.
So just going back to the old green case over there.
Yes.
Presumably you have a there's SO2 like.
Yes.
Right?
Yes.
And so probably there is an honest and factor equation in this world.
Yes. Yes. But the problem is yes, as usual, this computation is.
You just don't know the corresponding R-matrix.
Yes. Yes. The short answer is yes. There is one missing R-matrix which corresponds to both legs non-preferred. So it's I don't know it. Okay, so probably it can be calculated, but I haven't yet tried, and it must be. I guess it must be more complicated than this deceptively simple formula.
Is there something to representation here which guarantees that it exists? Or is there something like you learned the R-matrix from you?
Yeah, there is. Yeah. This one exists, yes. Yes.
The one that you commented up there was completely parallel. That got to be just the identifier.
These are metrics on the vertical legs. Yeah, it can be also obtained from the universal R-matrix without problem.
But I mean, it's just that that's kind of this R-matrix, but the one that
Yes. I think in my terminology it's the horizontal one, but no matter. Like I think yes, it's Smirnov's R-matrix, the Q deformation of Smirnov's R-matrix or whatever. Yes. The instant R-matrix it is also called. Yes. Okay, so let me just write this formula, but not in such detail as I wrote that upper one. So now you probably believe me that I have explicit formulas, but let me just write it in a little bit shorter notation. So I call it this R, which I have here, this orange and green one. I'd like to call it Hanany-Witten R-matrix. Why? Because if you look here, you have this one, this D5, and this NS5. The orange NS, yes, the orange NS5.
Something's wrong with the board. Some direction mixed up.
Yes.
I think you need to modify the call.
I guess so. I need to switch that. Okay.
Yeah, earlier you had all D5s on X.
I'm sorry, I'm always confused with this. It's a shame. Let me. If I do it like this, would it be consistent?
No, the problem is just that you see the entries are not like asymmetric in the middle column.
Ah, okay. Oh, sorry. Everything is a lot worse than I thought. I guess it should be like. This guy should sit here. Yeah. Sorry. Yeah. Now everything is completely mixed up, so fine. This I call Hanany-Witten for the reason that if you look at this D5 here and orange NS5 here, you see that this is precisely the setup Hanany-Witten have considered. And RT is the direction in which the D3 branes are going to live. But there are no D3 branes so far. So.
Actually, when they pass through each other, they're definitely. Never mind. Young Baxter, sorry.
Young Baxter is there.
Before we come to this the previous one.
Yes.
There is a sense in which the fork representation is already like an infinite tensor product of simple representation.
Yes.
And is that, are we really secretly breaking this sort of, we're secretly breaking fork representation with the simple representation?
Yeah, of course. If you look, what happens here in this language, which in the simpler, if you want, you can do this absolutely. So the fork representation you break in terms of the simple representation. And what happens is this character, which is a sum, it breaks down into sums over columns.
Right.
That's what. Which it can be viewed in different ways. The formula is consistent. So yeah, there is a simpler matrix which intertwines this vector representations. And yeah. Okay, so here the young Baxter is still there. So I tried to explain the origin of the name, but then I'd like to write the formula. The most important part of the formula is the prefactor f. Lambda mu, and then there is some exponent which so there is an exponent just as in that case, but with different coefficients, say Cn W minus n an like this, where Cn are explicit coefficients. Explicit coefficients. Now the prefactor f lambda mu plays the role of that prefactor there, n lambda mu, the Nekrasov prefactor. But here it's something different. And what is would be important for me that this f also introduces a selection rule. Selection rule, but a different one, a more stringent one. So f lambda mu is going to be 0 whenever lambda and mu are not interlacing. So mu is not only smaller than lambda, well, it's not bigger than lambda, but it cannot be too small either. So what does it mean interlacing? Here I use this, you see, this different sort of notation. So what does it mean when lambda interlaces mu? So if I draw lambda, so this is lambda diagram, then mu, let me draw it in green. Okay. Sorry. So let me draw the boxes, otherwise it will not be evident what the condition means. Suppose the boxes are something like this. Then the green diagram, it should sit inside here, inside the lambda diagram, but it cannot be lower than this one. So it's in between these two lines. So the diagram can be something like this. And here there is no choice. So let me write it as a formula now. So the formula is, this means that lambda 1 is less or equal mu 1, less or equal lambda 2, less or equal mu 2, less or equal, etc. So it's a more strong condition on lambda and mu. So mu is contained inside lambda, but also it cannot be too small, as you can see. And this is important. This combinatorics of this lambda and mu are very important for this operator, because otherwise it wouldn't satisfy this condition, more or less this condition. So this one is crucial for the functioning of this R-matrix. And it is also crucial for some, okay, so now this is basically all. I have an explicit form of this Cn coefficients also, but I'm not going to write them because I don't have, I guess I don't have enough time. So mathematically speaking, that's the result. Like one of the results is the explicit computation of this Hanany-Witten type R-matrix, which is the R-matrix acting in the product of horizontal green Fock space and vertical orange Fock space. That's it. Now, the properties of this RHW are really curious. So the properties of it, they follow, in fact, they follow the Hanany-Witten rules, in fact. So let me explain. What the Hanany-Witten rules are? The Hanany-Witten rules are that if you do something very similar to what I did when I did degeneration of this green picture, I sent delta tau here to 0, but in that case it cannot be resolved, but I can pass through 0. So there is, and in this case it gives rise to the inverse R. So there are again two possibilities. So there is a possibility like this and the possibility like that. Oops. RHW inverse. But this time they are related. They are not only inverse, but there is a funny relation on them. So it turns out that when, okay, according to string theory picture, if you pass this branes, one brane through each other, then a D3 brane has to be born. So there is a Hanany-Witten move, which says that if I adiabatically move these branes like this into this configuration, then here a D3 brane is born, which is stretched between these two branes. Now the question is, does it correspond to a crazy idea? Does it correspond to anything in representation theory? And then the answer is yes, because the D3 branes, they correspond to those simpler representations, the representations which Andrei mentioned. These are called the vector representation. Sorry. So where do they live in the picture? Let me show. So D5 branes, sorry, D3 branes. So they also have flavors. So D3 brane, it like spans one of those. So let me draw it like this. Spans one of those, and then it is a segment in R tau. And then again, as I told you, this S1 is going, everything is spanning. So this D3, it is precisely as in the Hanany-Witten setup. So when you pass this brane through, they have, when you have a, you see here, there is a dimension in which they coincide. So the D3 brane is going to live in that direction, and I haven't yet used this third color for this. So it's going to be a violet D3 brane. Sorry. So it's going to sit, it's going to appear here. But what it corresponds to as a representation? The answer is that there is, as if miraculously, there are representations of A called vector representations, V. And there are also three of them. So they can see the states in them are enumerated by like one-dimensional Young diagrams. Not two-dimensional, but one-dimensional. So the states there are like like states of the vortex partition function on the three-dimensional gauge theory. But the important point is that there are also intertwiners involving these V's. Okay, let me, what do I do? Okay, let me erase that one.
Sorry, why are we
Okay, one needs to, yes, one needs to do something here, because you see, I choose a color here according to what this D5 brane doesn't span. So this is kind of the only logical way to do it. Otherwise, you need, okay. And then you say that the color coding will be like this. I have green here, orange there, and then violet here. But the D3 brane, I have to color code according to the direction it does span, because there are other two. So I need to like label it by a single dimension which it does span. So hence this notation. Okay.
My question is like, we need to Hanany-Witten move.
Yeah. Yes.
That D3 is the purple.
Yeah. I need to write to draw it here as a purple.
And what we need the other.
Well, first of all, one doesn't need the Hanany-Witten rule. You can just add them to the picture, and this is something well defined, but I don't have much time to talk about. But to obtain them from the moving of D5 branes, one would need to introduce something like purple D5 or something like more ingredients. So that's the idea. And okay, let me continue for. Sorry. Absolutely, yes, yes. You know, that is everything. The world becomes colorful. You know, so there is the D3, the junction of D3 with a 5 brane corresponds to some intertwiner 2. Okay, so let me erase the solved blackboard. Again, so this just all the details you can forget, but the slogan remains. The slogan is whatever you draw in the brane diagram, in the brane picture, the junctions of branes, corresponds to something in the representation theory for the intertwiners and the representations. Or vice versa, if you know something like R-matrix, which exists for this algebra A, then it should mean something for the branes. It should mean some configuration of branes. So that's the rough outline of what is happening. So there exists a junction of D3 and D5 or NS5. A triple junction. Again, for geometric reasons, the colors here are fixed. So if you have something green, like the 5 brane here, the NS5 brane here is green, and then you can join it only with the D3 branes of these similar colors. So you can have something like this, or one can have the other possibility is like this. I'm sorry, so now the picture of dimensions is gone, but if you look what can join and what cannot join, you see that both of those branes, they share this C part of the geometry, so they can join. And if I say here the D3 brane, I want to join this D3 brane to D5, this is impossible because they don't share this part of the world volume. That's what this picture means. And this corresponds to vertex operators. So they also have the D3 branes. They have the spectral parameter, and this would be some vertex operators at W, acting on the green Fock space. And here, like another vertex operator, these are explicitly known again. And it turns out that like also the junction of this D3 brane with an NS5 brane like this, the green one or the orange one, these are also known. This can be described very explicitly. So if I have a diagram lambda sitting here, then what does this operator do to this diagram lambda? It transforms the state in the Fock space lambda into a tensor product of two states. One in the, so this belongs to F, right? And then there will be a tensor product of two states, one in F, another in this smaller space V. So in this space V, well, let me first say what is going to be here. So it will be lambda without lambda 1. Lambda 1 is the first column. So it's lambda with first column removed. And then the spectral parameter is going to be shifted. I'm not going to talk about. And here there will be a state with, okay, let me Let me write the spectral parameter here. Sorry. It will be like this. So I will have the states of this V, they are encoded by, well, the sort of fixed position states like in quantum mechanics, basically. So it's a state with a fixed position in like in complex W at this position. There's Q power lambda times W. And then there is the state in the Fock space with the smaller Young diagram with the first column removed and shifted spectral parameter. So this is what sits here, and this is the state here. So this is one operator, there is the other operator, versus operator. And it turns out that no, probably the final thing which I have time to talk about is how this Hanany-Witten move is realized. The Hanany-Witten move is an equality for the R-matrices, which is a true equality for operators. If I have this R-matrix like this, this is equal to the R-matrix like this. Oh, sorry. Again, so you can skip, if you don't like these physical arguments, you can skip all these explanations and just say that there is a true equality for R-matrices and intertwining operators. Sorry. Like this. So there is a invisible, probably, D3 brane. So there is this V representation here in the middle. And there is this operator, well, like it, but with the orange brane. And here is an R-matrix, Hanany-Witten R-matrix. And here is a convolution, a contraction of the R inverse times the combination of the intertwiners. I need to call them somehow. So let me call it phi, say this is phi vertical, and this is phi horizontal. Phi vertical tensor phi horizontal. Of course, summed over the intermediate state in the VQ. So this is a non-trivial property of this Hanany-Witten R-matrix, and okay, I still have 15 minutes, I guess, or like 10 minutes. Okay, this prefactor of the R-matrix, it plays a crucial role in this equality, because if you look at this two R-matrices, so R and R inverse, so this one, it contains F lambda mu. So there is a selection rule. This one contains, say, okay, G lambda mu. So for this one, lambda should interlace mu. But here, vice versa, lambda should be interlaced by mu. Here. So how comes that these two are equal? And the answer to this is that this operator, it removes first column of lambda. And then the combinatorics works that way, that if lambda interlaces mu, then lambda without lambda 1 is interlaced by mu. So this is the combinatorical sort of one of the parts of the proof that this is a true identity. It turns out to be a true identity. So that's the main part. And then there are some applications which I'm probably not going to talk about. There are some applications of this formalism, well, somewhere. Maybe I can just list what one can do with it. and then okay, I erase this crazy expression, and then this will be some kind of conclusions, I guess. So applications. The first one is that so D3 branes stretched between D5s and NS5s give 3D gauge theories. So the properties of the gauge theories, they can be deduced from the properties of these intertwiners. And let me just mention that the matrix elements of this, the vacuum matrix elements of these intertwiners, they are going to be equal to 3D partition functions on D2 times S1 of this gauge theories. And of course, like this Hanany-Witten moves and rules, they are satisfied. So the rule, the Hanany-Witten rule is that you cannot, for example, that you not more than one D3 brane can be stretched between a given pair of D5 and NS5, and the corresponding intertwiner automatically vanishes, it turns out. So satisfies the Hanany-Witten rules moves. Okay. And the second application of this is a very nice expression for QQ characters. It turns out that this, if you have a green picture, so let me redraw. If you have a green picture corresponding to a 5D gauge theory, something like this, then you can add a background orange brane, and then put some non-trivial states here, like box and empty. And this would be some observable in the gauge theory. And it turns out that this is precisely what is called the X observable. The X, so there is a spectral parameter here, of course. So it is going to be X of W in the 5D gauge theory. So again, it's just a kind of to give you a flavor of what the expressions are going to look like. And it turns out that there is a simple expression for higher. So this is the kind of fundamental QQ character. And then for higher, one just needs to consider different states here in the representation. And the final point, the final application, or the kind of the thing which one can do with it, to play with it, is and one can obtain k-theoretic vertex from a combination of RHW. You see, there was this funny combinatorial property that the Young diagrams on the legs, the matrix element forced them to interlace. So this lambda and mu were forced to be interlacing. And if one contracts a bunch of these R-matrices, one can look at it as slices of a 3D Young diagram. Well, then the question is what one can associate to a 3D Young diagram, which kind of weight? Well, the natural weight is, of course, the k-theoretic weight of the this k-theoretic vertex. And it turns out that this combination of R-matrices, the contraction of R-matrices, it does give, it does reproduce this way. It gives the same weight. So again, about this I don't have time to talk, but these are, I think, some interesting points about this R-matrix game. Thank you very much.
Questions?
So you think there's some four-dimensional time theory?
Four-dimensional Chern-Simons theory with a huge, like an infinite gauge group like this A, or something like that. Well, again, it's a very naive idea, but it looks like that there are these pictures with crossing of branes in 3D space, but there are also the spectral parameters. So one probably needs a 4D Chern-Simons for this. That's like my naive guess. But then what are the representations on this list?
If you didn't have a UU of DL1 half by UU of DLN half,
Okay.
then there is a homomorphic you want sometimes, yeah, that's enough.
Okay.
So you want some loop group version of that?
Yes, but I have no idea how to construct it, of course, just for now. But logically, it should be a theory should look like this, like a 4D Chern-Simons with a loop group, gauge group.
Well, for the original one, it ended up being a calculation, which was the very surprising one, that from this fairly stupid looking, honestly, homomorphic Chern-Simons theory, you could actually calculate the elliptic R-matrices, which are fairly fancy things. So there must be, since you know the R-matrices, there must be some kind of a calculation that's going to let you deduce. And the calculation involves finding the average.
I see. So it's corrections like
Yeah,
you calculate.
So maybe one could actually make that precise. That was very.
Yeah, absolutely.
Then you could actually understand
how it works. Yeah. There is absolutely. I totally agree. The short answer is I agree. It would be extremely interesting. Yes. But I don't know any details yet.
We have a tiny question. So
Yes.
this Hanany-Witten equation can replace the board.
Yes. One moment.
You read the equation from right to left. Yeah. Something.
Yes.
So the green line, outline, and this integrate connecting. Right?
This one.
Yeah.
Yes.
And you move the other way, and the integrate just disappear.
Yes.
With like a bigger original picture where the machine is isolation.
You mean like can I zoom on that part without the R-matrix? You mean, or something like that? Like.
No, I was saying like if we read the right-hand side, it has some integrate connecting to branes.
Yeah.
Then somehow past each other.
Yeah.
The integrate just cancels and die.
Like what happens in the intermediate here? In the like when they.
I guess my general question is like suppose I give you some arbitrary integrate connecting these two guys.
Yeah. Yeah.
Are you able to connect what get created and what get cancelled?
Yeah, this is okay. The short answer I think is that you can always deduce what happened because, well, first of all, there are not too many choices. There is really like, for example, if you have an orange one and the green one, then the purple one is created. If you have a green one, there is no such identity. If you have a green one and the green one, it's not a Hanany-Witten setup. So the branes have different, they span different directions. And there is no identity like this. So if you have a green and green passing through, this doesn't work. But if you have different colors, then you just like get the one which is the color which the third color, and that's it. Sorry, let me just mention like about the cancellations. What happens if you draw something like this? Is I mentioned it in words, but let me just mention it. Draw the corresponding picture that which probably is part of the answer to your question is that, for example, if you have it happens so that you have a pair of T3 branes having here. So this is 0. This is called the Hanany-Witten rule. So that not more than one D3 brane can be stretched between a given pair of like D5 and NS5, like orange D5 and green NS5. Like there is only one or 0 can be stretched between. So that's the idea. Thank you.